Okay, so I'm Teresa. My pronouns are she, her, and I coordinate SPEC's Farmland Ecosystem Service project, and I work with the SPEC food team as well. So I want to acknowledge that I'm greeting you from the unceded territory of the Musqueam, Squamish, and Tsleil-Waututh Nations in what's known as Vancouver. Just as a reminder, unceded means that the land is illegally occupied. And there have never been any treaties where I am. I think for those of us who are not Indigenous, we need to recognize how colonialism has affected Indigenous ways of being. Today, because we'll be talking about water and irrigation, I wanted to just highlight some of the inequalities relating to access to clean water to many First Nation communities. And so I'm going to share a resource about that in the chat. It's a map story on ArcGIS. It is a little bit outdated. It's from 2021, but I think that it's really well researched and it has a great intro and information. So I think it's worth taking a look if you're interested. And also it doesn't appear to include any data from the territories, just the provinces, but I think there's a lot of good information on here. And if you're curious about like any updates, now that it's 2023, you can look into specific nations. So a little background about SPEC for those of you who aren't familiar. We work to develop practical solutions for urban sustainability, and we're a charity founded in 1969. The program that I run is the Farmland Ecosystem Services Program, but SPEC also does work in areas of energy, transportation, waste, and climate change. We're in our last session of our 10th annual Small Farm Sessions. And this year we received support from the Vancouver Foundation and the Enswell Foundation to put on these sessions. So I'm very grateful for their support. Today we're going to have our second water-related session with Bruce Naka, and I'm really excited to be able to have him join us today. So Bruce has been involved in irrigation design and implementation for over 30 years. He is really super experienced, covering all facets of irrigation systems from sports field and golf courses all the way to large-scale ag systems. Bruce is certified by the Irrigation Industry Association of BC in a lot of things, including commercial turf sprinkler and ag sprinkler and drip irrigation, and he's a certified irrigation scheduler. Bruce has assisted well owners in their application for groundwater licensing, and he served on the North Okanagan Drought Response Committee, the North Okanagan Agricultural Advisory Board, the Okanagan Water Stewardship Council, and as president of the IIABC from 2017 to 2018. In 2015, Bruce established an irrigation consulting company focused on efficiency in irrigation design and system planning. So a true expert with a wealth of experience in this field. So without further ado, I'll pass it over to you, Bruce.
Thank you, Teresa. Welcome, everyone. It's going to be a relatively casual affair today. I think we will have one little breakout, maybe somewhere along the line for questions that are, eager questions that they want to get out while the slide is hot. But at the end, we will have another session as well. So keep that in mind. So today we're here to talk to you about the anatomy of an efficient irrigation system. Now, the first thing about an efficient irrigation system, the first thing that is necessary is planning, and perhaps a drawing up of a map is a very helpful tool to start off with. Okay, so what we want to do is we want to look at maybe developing an irrigation plan and a design for your property. So here we have a blank slate of paper here. What we want to do is we want to identify where your water is coming from, be it from a water privilege source or be it from a pump or a well, but we want to determine that. We want to determine the acreage of that property that you potentially would like to farm. We want to evaluate your soil textures because they obviously have different holding capacities. We want to determine obviously what you want to grow into these different areas, and how valuable that would be. And then we're going to start our irrigation plan. We're going to draw it out to scale on a map, indicating on it where all obstructions are, buildings, roadways, trees, etc., so that we know we can't plant, or if we're trying to determine a pathway of where piping is going to go, we don't want to put it through an area that is going to make the map off right to begin with. So those are all important things that we have on that. Once we've established that, we would plot for irrigation purposes where our main line is going to go. Your main line is from your source of water. It is going to be the main carrier pipe, or is going to carry your water to your various areas that you have planted throughout, obviously. Okay, so we are going to look at your water capabilities, where your sources are from. So we have two sources of water capable. We're going to be looking at water that is going to be pumped, or we're going to look at purveyed water. So if you're using a pumping system, it's important to know a little bit about the well. If you're new to a piece of property, you can usually get something called a well log. A well log is something that a well driller or a pump installer has produced. It's going to tell where your pump is, how deep it is down, and potentially what the power is available and how much water is available. That's a very handy tool to have. Failing that, because there are some older wells out there that may not have that, you need to do some research. You need to look at what is in there for a pump. What is the total dynamic head of that pump? So what the total dynamic head is, how hard does that pump have to work to bring that pressure for your sprinklers to work? We need to know these sort of things. You can usually get a pump curve or something like that. If you know the model of the pump, take it to your local distributor or look it up online. You can usually find curves for these pumps. So you have some sort of indication of how much water you have available, because a lot of people think, well, I got a pump, I got a well, here I go. But you have to put it all together. Because you have water, do you have enough to facilitate irrigating the entire area? Or maybe you'll have to step it down if you have a lack of water or too small a pump. So these things will have to fit together before you follow. If you have a purveyed water system, that means that you have water that's being supplied to you from an irrigation district or from a municipality. A lot easier to work with, obviously, because the pump is right there, just like your house. Open up a tap and away you go. The challenge for that is, if it is agricultural water, you have to make sure that the former owner or has allocated enough of the acreage to agricultural water that he has available. Because you have 10 acres and the customer has decided that they only wanted to irrigate a couple of acres, you probably won't have enough water to irrigate most of that 10 acres. You want to keep that in mind. Rule of thumb, if you're down in the coastal areas, if you were to use 4.5 to 5 gallons per minute per acre, it's a good starting point based on the climate for down in the coastal area. For purveyed water systems, pipe sizing is important. So from wherever your connection is, you want to know what size is the outlet that they're supplying to you, so you know that you would have adequate amount of water coming out of there. And you want to know the pressure, because that's like I said, same as a pump, we need that pressure. Depending on the type of system you have, it will vary, but we have to keep that in mind. A good way to test that, if you have no other devices, it's very simple. A pressure gauge you can purchase at any hardware or your irrigation supply store. And you can, for determining your flow, if you have an outlet at the beginning of your system, you get a 5-gallon bucket and time how long it takes to fill that bucket. So if you get if you got a 1-gallon bucket and it took a minute to fill it, you're only getting 1 gallon per minute. So a 5-gallon bucket will be a best way for you to test that. As I said earlier, pressure is a very important thing. We want to determine that pressure, and you want to be cognizant of, if you have a high elevation change, be it up or down, that's going to increase or decrease your pressure. So for example, if your outlet for your property was at the very bottom of the property and the property rose in elevation by 100 feet, you would lose 43 pounds. You would lose 43 pounds of pressure going from top to bottom. For every 100 feet, of rise in elevation, you're going to lose 43 feet. For every drop in elevation of 100 feet, you're going to gain 43 pounds of pressure. Keep that in mind. Okay, this little diagram I have here, I'm just going to get rid of that for now. So on this little diagram that we have here, it's giving you some idea of a property. I just want to get, oh, okay. Well, I won't be able to get rid of this at the bottom of my screen. So at the bottom of the bottom right-hand corner of your property, you're going to see well. I'm just assuming this to be a well system. We have a well located down at the very bottom. On the right-hand side of the property, you'll see South Road noted on it. You should always have an arrow indicating the direction. So we have a north at the very bottom here, indicating where north is. So we'll be able to orient to where we are. But from our well down at the bottom here, down here, you're going to have, that's where our water is located from. That's where we're starting from. That's where we've determined how much water we have available and the pressure that we have. You'll notice on this piece of property that I've indicated in various areas. Here's plus 25. That means it rose 25 feet in elevation from our starting point back here along South Road is that's the starting point. So I'm calling that zero elevation. At the bottom left of the map, just before the house, there's an indication there. It's 20 feet in elevation. And then you'll see at the very north end of the property, at the top and the bottom, it's 35 feet in elevation. So from where our well is, we know that that pump has to work hard enough to pump up 35 feet in elevation to get water to the top end of it. No, I just have arbitrarily some facts about this that we've got. I've assumed this property to be in the Sumas area. So Sumas area, I know that we're going to require 4.5 gallons per minute of water per acre in order to irrigate it. This entire property here is 6.2 acres. Of that 6.2 acres, we've done a little bit of work and we've determined some soil types, which I'll go over soil types in a few minutes here. We've determined some soil types based on the crop depth, the root depth, and we've identified them on here. And then we've looked at the areas. Well, this area behind the house here, long, narrow area, I think originally I put that as pasture, but I'm going to change that and we're going to assume that to be corn. We've got an acre where we might be able to plant corn in here. We have another piece on the east and west side of the house. One side, I thought we could put a 1/4 acre, 0.27 of an acre of strawberries in. On the other side, same of garlic. Going south on this property, the very south east side of the property, I'm looking at one planting of raspberries, 0.44 of an acre of raspberries. And it has a sandy loam soil. And then if we go further south, same sized acreage with 0.44 acres, it has a clay soil. So they have heavier soil at the bottom here. We've reciprocated that with blueberries, 0.44 of an acre of each, both with sandy loam and clay soils. We've dropped down another to a section where we're going to plant variable vegetables, again, 0.44 and 44 of an acre, with the sandy loam soil on one side and clay on the other. And on the very bottom, we have a sandy loam soil where we're going to grow tomatoes, and another one in clay, one in the sandy loam soils. So doing the math on all that, what we have here is a total of 5 acres of plantable area out of the 6.2 acres. The 5 acres at 4.5 gallons per minute works out to about 22.5 gallons per minute of water we would require to irrigate that. Round it off to round figures. Let's say we need 25 gallons per minute in order to irrigate this entire field. You need to put a main line in, and I can't see this on my drawing here. I hope you can. It's the dark blue line on the bottom of your map. Anybody there, does that show up on your map so I can orient? Teresa, does that show up on the map?
No, we can't see it. It looks to be cut off. Yeah.
Okay. Yeah, I can't do any adjustments on here. I'm sorry, I apologize about that. But there is a blue line. If you look at in front of the house, and if you look at another line halfway down between the raspberries, you'll see another blue line.
Mhm.
That indicates main line. Now, the important thing about this today is this blue main line is running right along the west border. So that's the bottom of the page. It's going to be a main line that's going to run all the way from north to south. So it's going to start right at the road, and it's going to go all the way up, all the way to the edge down here of the cornfield. And then it has sub-mains, which are going up here and here. Why am I putting all of these lines in, you might ask? The reason for that is, as I mentioned earlier, we are going in elevation from 0 up to 25 feet. So it's rising in elevation this way, all the way up to 35 feet this way. And so if you had a contour, this would be a 0 contour. Your 25 foot contour would probably be something like that. And then your 35 would be flat up here. So when you are supplying water to zones, especially with drip and micro, which I am, and we'll be talking about this later, I am going to suggest that to be the irrigation system choice in a few of these crops. You always want to feed it downhill because we're dealing with low pressure. It's a challenge if you're feeding uphill. So we're always wanting to feed downhill, hence the need of a sub-main here and here. But we're going to zone this up and we're going to break it. The only other thing that's key here is the size of that main line. If, without going into it a lot of detail, this is a starter course today. For 25 gallons per minute of flow, it is necessary to have a minimum of a 1 1/4 inch pipe, maximum of 1 1/2 inch pipe in order to feed enough water to these areas. And I want to have the ability at any given point of this place to use my maximum amount of water at that point. Sometimes people say, well, I'll be irrigating the raspberries and the blueberries and the vegetables at the same time, all smaller flows, and we'll do it that way. But your main line could reduce in size as the flows go down. But what I'm suggesting is we're going to plan ahead that we can use all our water anywhere, and we're going to have 1 1/2 inch pipe to all areas. In regards to the soils, like I said, I'll talk to you about soils in a second. But in areas, a sandy soil is going to pass water through it a lot quicker because of sand content, versus a clay, very tight particles in the clay soil, that the water it'll hold a lot more water. When you're irrigating it, if you have varying soil types on the same zone, it means that some areas will be getting a lot more water than other areas. So that's why I've decided in this plan to break up even if the same crop, raspberries, because the same crops, again, should be irrigated together. This is all raspberries, but I'm suggesting we water this half with this zone valve here, that's the zone valve, this zone valve. Same thing follows all the way through. So that's the logic for the soils in that. Again, this is a very brief one, but it's giving you some ideology. You have this with you, and if you want to ask me questions at a later date to elaborate on this, by all means. The header line, as is indicated by this red line, joins up the zone. So this zone here, for example, here's your main line, here's your zone valve. It goes to what's called the header line, and that's the line that's going to feed the drip irrigation. In this case here, goes along here, and then your drip lines would run this way across the property. Quickly about the types of sprinklers that you could use. If we were irrigating corn, you want to use a big sprinkler. You can get mini traveling guns, for example. You might want to use something like that in the corn. In strawberries, garlic, vegetables, a lot of them, some of the annual crops, let's say the strawberries are an annual, and even in the tomatoes, you may want to go to a drip tape. A drip tape is less expensive. It has emitters at varying spacing between it, depending on your crop and what you require, and it is less money. For something like your raspberries, your blueberries, you may want to go to a more permanent type of a drip irrigation system. You might want to use inline drip irrigation tubing that's far more robust. The pressures it'll handle is more, and it's more designed for a longer period of time. Not saying that you couldn't use the same type of heavier wall that I'm suggesting for the raspberries and blueberries everywhere, but over a period of time, you may find as you're changing your vegetables that it might be better to go to a tape. That's it for our quick plan there.
Bruce, can I just interrupt with a question? Someone asked if you could clarify I think when you were saying the diameter of the pipes, what was the gallons per minute?
Oh, okay. Yes, I said 25 gallons per minute is what I was basing that on, and that was based on the 5 acres that we were going to plant of this property. And of that, when I say 5 acres, that leaves the rest is hardscape. And unless you think you can transition that, if you wanted to make it 6 acres, you could. But the 5 acres is going to be your hard amount of planted area. So 5 acres times 4.5 gallons per minute per acre in sumac comes to 22.5 gallons per minute. And I suggested we go up to 25 gallons per minute as our base to round it off. Okay.
Okay, great. Thank you.
Okay, soils. I won't spend a lot of time on soils. I am going to suggest something to you. If as far as testing of soil textures, it can be very easy, but I think there's a simplified guide out. I was involved with another fella, and we were doing a project in the Okanagan, which we just completed. And part of it was we had to develop some case studies as well as some fact sheets. The fact sheets were produced. My cohort on this did an exceptional job of creating some fact sheets. He goes right through in detail how he would suggest you test your soil textures. So I emphasize that's a good way to go about it. So all the way from getting the large rocks out to moistening the soil, rolling it in your hand, trying to get it into a ribbon. If it won't make into anything, it's going to be a sandy soil, and then it progresses down. So I think that'll be available on the website. Probably you'll be able to get that from the CAI, Climate Action Initiative website, or you will be able to get it from IAF, the Agricultural Foundation. So those would be 2 sites where you'll be able to get that. On your soils, you can see on your soil triangle, you have groups: loamy sand, sandy loam, clay loam, so on, all the way to your silts and your silt loams. We have your different soils, and if you can determine the textures of your different soils, you need to know, in order to determine the amount of water that your soil will hold, which is the important factor, because that's how you're going to determine how much water you have to give your plants. You want to determine if it's sandy soil, sandy loam soil, silt. There are a bunch of variables in between, but I wanted to minimize it. So you'll see here a sandy soil will hold 1 inch of water per foot of soil. You go down to the bottom here, and on a heavier soil like a clay, it will hold up to 2.5 inches of water per foot of soil. That's a significant difference. When you want to determine your soil water holding content, what you want to look at is you have to determine your maximum soil water deficit, which is going to be a factor of your soil type times the root zone. So depending on what your root zone is, if you had, say you were growing your corn or something like that, you might have a 3-foot active root zone on it, 2-foot I think corn is. So you would take your type of your soil times your root zone of your crop times the crop availability. Every crop has got a different amount of availability of the water that's available to the plant. So for an example of how that would work, if we were to take a sandy loam soil, you would have 1.5 inches of holding capacity. And we're growing grapes, you have a 4-foot active root zone. And the availability for grapes is 40%. So if you multiply that out, 1.5 times 4 is 6, times 0.4 means that you would have 2.4 inches maximum water to be removed by the crop from the soil prior to irrigation required. So that's how often you would have to irrigate. don't beleaguer a lot of time on that right at the moment here. It's just for the concept that I'm going through that. Okay, components of an irrigation system. An irrigation system, what is an irrigation system doing is we want to get an efficient irrigation system. That's one that's going to maximize available water for use on its crops as expressed as a percentage. That's how you determine how efficient the system is. Irregardless of the type of irrigation system that you have installed, they have a lot of common items from your point of connection out to the field. There's a lot of the same items used in irregardless of the size of the system, the crops you're growing. There are some very common features of them. For example, from where you start, you're always starting with either your pump or your connection from your water from your district or from your permitted water source. The first item nowadays on most systems is a water meter. Water meter is the first item. It's usually followed by a backflow preventer. Anytime you have cross connect to where domestic water could also be supplied, you would need a backflow preventer. From there, you're going to be going out somewhere along the line. A lot of people may want to introduce fertilizers to the system. And if you have drip irrigation and micro irrigation, that's the most efficient method of getting down your fertilizers into your crops. If you are using drip irrigation systems and likes of that, you probably need a filter system. The filter system is going to be fine as necessary, dependent on how large the outlets are on your sprinklers or your drip devices. And from there, some other things, isolation valves are necessary in different areas. You can shut off parts of your main line to repair other parts if there's a break on the line. Pressure gauges are a very, very useful tool. I'll show you in a second a couple of demonstrations of where they could go, but a pressure gauge is a good way of determining if you know what your pressure is at the beginning of the system, the pressure is significantly lower at another point, where has that pressure gone? You know, it's a good indication how you can try and identify where a leak is. From there, you're going to go to a mainline network. Same thing, regardless of the type of system, you need a main line going out, which is going to have outlets on it to either valves, be them electric valves or manual valves, or if it's a bigger system where you just have hydrants where you connect onto aluminum pipe, you're going to need that all of that off of a main line. So a main line is an important element on your system, as well as air relief valves. Air relief valves are very vital to a system, which a lot of earlier systems do not have. That's the makeup of what you're going to need to start an irrigation. Now I want to just break it down to some of the different components that are necessary, why they're necessary, and some of the importance of them. So this diagram here is not able for me to change the size of it on here. On this one system here, you have on the left-hand side, what do you, on your, what you have there, Teresa, it shows from number 4 to number 11, left to right numbers?
Yeah, that's right. I think we can see the same as you, Bruce, from 4 to 11.
Okay, I had minimized it on my drawing so that it was all on there, but for whatever reason, without fiddling around with it for a long period of time, I can't do that. So anyway, I know the drawing well enough from heart that we can go. So point of connection doesn't have to look exactly like this, but in my career, so many times I would be drawing on cardboard boxes or on something. Okay, well, how do I put all this together? And so I developed a few different ones, but one that I use a lot of the time. And it's important to look at, I think the first thing, which is actually, if you look at the bottom, if I can move this at all, no, I can't. At the very bottom of this, it talks about the type of material that you use in a point of connection. And the important thing to read there is it's a good idea for all points of connection to either be metal or a minimum of Schedule 80, which is the thickest wall of PVC pipe you can get. Why is that? Number one, unless it's in a building, if it's open to the sun, UV rays will eventually break down PVC pipes. It's far superior to what it was years ago, but that's still a problem exists. Good idea. If you're working with a pipe wrench or some heavy wrench, you drop it on plastic pipe, it's liable to break regardless. So always good to have a good thick pipe when what you're irrigating with. Your point of connection, generally most of the components will be the same size as the piping network that you have. Some of the items such as filters and like that may be larger. I'll go through that in a minute. At the very bottom here on the left side, you have your water supply coming up. Item number one listed on my legend is the point of connection drain. So at the very bottom there, you want to be able to drain this upright pipe, which is coming up to number 4. That upright pipe has on it an isolation valve, which is item number 1, and the sorry, that's item number 2. Looking at it this way, my drain is number 1. Number 2 is a ball valve. You want to be able to isolate the whole system going out without going back to your city curb or something like that to shut the water off. So it's always good to have an isolation valve here. That one would be a ball valve. At the very top here, where we're teeing off to go into our into item number 4, I have a live tap, and that's just a hose tap, and I'll explain why in a second. So that is item number 3. Item number 4 is your water meter. Water meters, they like at the beginning of a system. The key to installing a water meter is for a majority of water meters, you need to put in 4 pipe diameters ahead of a meter and 2 pipe diameters after meter. What does that mean? That means if you had a 1-inch pipe, you would have to leave 4 inches of space before the meter and 2 inches of space after your meter of blank pipe, no elbows or anything on it. Why do you need that? You need that for the accuracy of the meter. It creates too much turbulence if you don't have that straight pipe, if you had an elbow or something like that sooner. But you need that much to straighten the water out, so you're going to get more accuracy out of your meter. So 4 pipe diameters before, 2 after. Item number 5 are unions, and the unions are simply so that you can take parts of your system out for repairs or replacement. Number 5 is a union, and here, and there is another one that is no, that's sorry, just the 3 of them. Three union items would be required along with. Item number 6 is the backflow preventer. A backflow preventer is necessary anytime you're hooking up to pervade water. If you're hooking up to groundwater, it's a good idea as well, so that there's no potential of you any contaminants back into your aquifer. But a backflow preventer is always necessary on a system. It has the minimum one you'd require would have 2 check valves in series. So if one fails, the other one will operate. If you're chemigating or fertigating, you would have to be more elaborate. You would probably have to use what's called the reduced pressure double check valve in here. That's a device that is required on a system. So this order of that's going along here is a good suggested order of all these components to go. Item number 7 is simply a metal nipple with a brass valve on top of it, and that is your main blowout connection. So in the interior here, we're always blowing out our system down there. I'd say 80% of all irrigation are winterized as well. So you need a place to winterize from. That's item number 7 here. You recall I mentioned a live tap, item number 3, which is up here in the part you can't see. How terrible. Sorry about that. Why you have that is backflow preventers are expensive devices. If you were to continuously blow air through them, you're going to prematurely wear out the seals on your check valve assemblies. So you don't want to continuously blow through this backflow preventer and have to replace the check valves prematurely. What we usually recommend is to do a quick burp of air from this live tap here through your backflow preventer, exhausting it out of number 7, your big ball valve. And then after you finish that, shut your main valve off here, item number 2. And at that point, you could close off the valve. There's 2 valves on all these backflow preventers. You would close down this valve off and blow your system up from this point on. Item number 8 are pressure gauges. If you have item number 9 is a filter, and this is one that is suggested for this particular application. If you have a pressure gauge on either side of a filter, it's going to tell you if this one here is going to give your full supply water pressure. This one on the downstream side of the filter, your second gauge, right there, is going to give you pressure after it's gone through a filter. So if the filter is plugged with dirty water, so that your water pressure is lowered significantly, I say if your pressure is more than 10 pounds of difference between this gauge and this gauge, the first gauge and the second gauge, time to clean the filter. So when you clean your filter to begin with, this gauge and this gauge should read very close to the same. As it gets dirtier, the second gauge is going to drop. Then without taking it apart, you already know that it's time to clean a filter. That's the benefit of gauges. Gauges are an excellent method to determine to do a lot of troubleshooting. So pressure gauges are important. Item number 11 here, which you only see part of, is a suggested method of putting in your fertilizers or chemicals into your chemigation or fertigation. The easiest way to do it, and this way would be plumbing, is utilizing a venturi nozzle or creating pressure differential between a valve here and here. So what we're trying to do is create a higher pressure coming in this way, and then on the bottom side of it, after the venturi nozzle, and the throttle valve here, that would be throttle on the other side of it. Because of the difference in pressure here to here, it would cause the venturi nozzle to suck your chemical up into the system and enter into your system. Item number 10 is the valve again, but this item here should probably not be a gate valve or a ball valve because they are not designed for throttling. Throttling is method to throttle down your flow so that we can create a high-low pressure situation like we're trying to do here. So a globe valve is your best item to do that. If you require a pressure reducing system because you have too high a pressure from your pervade water source, that would be the good place for your pressure reducing valve to go as well. The last item, which is not shown on this plan here, is item number 12. And item number 12 is an air relief valve. You would want a continuously acting air relief valve on the system, and it would go on at that location. That's the general idea. I think Teresa has a copy of this PowerPoint, and on that one there, you'll see the full size of the point of connection on there. So if you wanted to utilize that as something to copy, that would be the place to get it from. Water meters. Water meters, I showed where they go on the system. They can be, a lot of people see water meter as something that irrigation cities put on as a method of, it's just a great way to increase cash flow by charging you for your water. That maybe has some truth to it, but also I think it's the only way that you're going to know how much water you're using. It's the only way you're going to be able to know if you are being efficient with your water use. A lot of irrigation districts in the Okanagan, for example, for agricultural customers today are giving you an allocation that you have, and that is the amount of water that you are allowed to use over the course of a season. And if you're to exceed that, the threat is that eventually you will be charged accordingly. So the water meter can be a tool. These little red dials that are on the side here, they will, if one of them is continuously moving around, you probably know if you've seen that on your house, that means that with no water running in the house or no water running out in the field, and if that little red dial is going around and around, it means that you have a leak in your system. Good way to determine your leak in the system. The flow meter can be used if you time, most of them nowadays are in cubic meters, but if you time the amount of time it takes to get a specific amount of water, a cubic meter of water, you time how long it is, and it's giving you your flow rate, which you could change to gallons per minute by calculating it out. So this can be a useful tool to detect leaks, to monitor how much water you're using. it is good to have. If you don't need a water meter, there are other devices, flow sensors and flow meters, which I highly recommend. You can get flow sensors, for example, which I'll have a photo of in some later slides, but a flow meter will give you a flow by, if you had say a control system on a controller, you could have it identify the flow of each zone. And then when that flow is exceeded by more than 15%, and that's actually, you can change that amount, it will automatically shut down a given zone, meaning that if there's a leak or there's something wrong in that zone, instead of watering it and wasting the water, it would shut the zone down. So a flow sensor is going to give you that flow by, and it will read out on your controller how much water flow is to each zone. Filters are really important in micro irrigation, drip irrigation, but even on, if you're using sprinklers, if you have very turbid water, good idea to stop those contaminants out of the system versus going downstream and having them plugged down. So there's a couple key things that are important. Remember, I was saying before that your point of connection is going to be the area, pardon me, would be the area that would be the minimum size. What I would suggest you make all of the components in your main connection. What I would advocate on a filter system is to have a filter system with enough surface area. Surface area is the area of a screen in this case here. This is a screen in this filter. So this screen surface area is the amount of filter area that you have available. So if you have a 1-inch outlet on your system, let's say, and you had a 1-inch filter, and that is what you use to irrigate or to filter your system. What I would say to you is, depending on how coarse this screen is in your system, and that's going to be determined by what you're irrigating with. If it's with big sprinklers, not an issue. If it's with finer drip, you need it fine enough that you would have to be 10th. The screen outlets would have to be the 10th of the size of the orifice that you have to minimize pluggage problems. So if you have a manual clean filter, well, a lot of times what I'll recommend, if you had a 1-inch service, for example, I would look at putting a larger filter, maybe an 1.5-inch filter in that area with larger surface area, so it's not going to plug up as quick. If you had a 1-inch screen and you had very turbid water, you might be cleaning that sucker 4 times a day. Nobody has the time for that. So my goal on a manual clean system is to go large enough to facilitate maybe having to only clean that filter once a week. Granted, you can get yourself some automatic flushing filters, very elaborate. I'm not going to go into detail today, but there are a lot of different self-flushing filters available. If you're going on to a lot larger system, you can even go to sand filters and the likes of that, which are one of the best ways of filtering. So filter sizing in general, if you're going with a manual clean filter, a lot of surface area, and going to a fine enough filter to facilitate 1/10 of the size of the orifice, should be 1/10 the size of your outlets out in the field. Okay, on a main line, I'm not going to spend a lot of time on a main line other than to say that this has been caused by a vacuum. That's why that pipe has collapsed here. A vacuum, I was talking about air relief valves. Air relief valves, I'm going from backwards to forwards here, but an air relief valve is one of the most crucial devices on the main line. A short one for a small farm may not be as important, but keep in mind that if you have what's called a continuously acting air relief valve on the system, it's going to help your system operate that much more efficiently for a lot of different reasons. If you're filling the main line up with water, the air relief valve is going to evacuate all of the air out of the main line at that wherever it's located, so that it can more quickly fill that line up. If you're emptying a line, the air relief valve is going to allow air into the line, so it's going to be able to help you to empty the line quicker. Air relief valves generally are going to evacuate air out of a line if you have air in a main line, which usually will be located at high points on your main, so like on that first diagram I showed you of a field that had 35 feet in elevation change, at the very top of that field, you should have an air relief valve to evacuate that air, so it's not going to cause problems in your system. One of the biggest problems with air in a line is it's going to cause something called water hammer or surging, and that happens when water is flowing in one direction in a pipe, and then you shut the valve quickly, be it a ball valve, which is the quickest of the closing of valves, or an electric valve. It'll shut the system down, and the water flow going in one direction with that quick shutdown can increase the velocity of that water going backwards at 2.5 times that as it's going forward. So if you had 100 pounds of pressure that was flowing through at, the surge or hammer could be 250 pounds coming back at it. So what does that do? That's causing a lot of problems on T's and elbows and things like that where you're getting breaking. So size of the piping is important. Too small a pipe, you're going to have more water hammering. If you got air in the line, it's going to cause more hammering. So those are two things to look at. Just want to spend a quick second talking about main lines. I already talked about sizing of a main line. It's very important that you will have a large enough main line based on the flow that you have available. It's really important to know the pressure rating of the pipe and the fittings that you're using. If you're using the white PVC piping, a lot of people previously were using 160-pound pipe for pipes larger than 1 1/4 inch, say up to 3 inch, and for smaller sizes, 3/4 and 1 inch might be rated at 200 pounds of pressure. If your pressure is high or there's any chances of surging in that, what a lot of people are doing right now is they're going to what's called a Schedule 40 PVC pipe, which is usually a lot thicker wall with a higher pressure rating. They're using that for their main lines, and then when they go to the laterals, they could go to something like the Class 200s. The material of the piping is important. Poly pipes, typically your standard 75-pound, 100-pound poly isn't rated as a higher pressure. Be careful of that, especially at the fittings where there's usually a gear clamp or something like that, which can blow apart. So material of your piping is important. Isolation valves, I talked a little bit about isolation valves on that preliminary diagram. I neglected to point that out, but any time that your main line goes in a couple of different directions, an isolation valve is a good idea, so that if you have a break on that main line at one far end, you're not going to have to shut your whole main line down in order to make that repair. Depth of burial of mains while your piping is important. If your burial is too shallow, you're going to, and especially if you're going over it with heavy equipment, you're going to end up breaking it. Sand bedding is a great idea. You don't want to have rocks in the soil that are going to be protruding and scraping against your pipes, breaking them. Sand bed is a great idea. Sleeving, if you are crossing where you have vehicular traffic crossing, say on a driveway or something like that, if there's potential because you have large trucks coming through your property, you want to make sure that that sleeve is strong enough to withstand the extra weights involved. If we're talking a sleeve on PVC piping, what a lot of people will use is a larger PVC pipe to do that with. I would recommend making sure it's a minimum of a Schedule 40 sleeve that's going over top of your pipe. And usually a sleeve is twice the diameter of the pipe it's covering. So if you have a 1-inch pipe, you should have a minimum of a 2-inch sleeve that pipe is going to go inside of it. Air relief valves we've already talked about. Okay, there is the air relief valves, and we're not going to go. The other thing I should mention about air relief valves on a system, as I said before, they should be at the high points of the system. An air relief valve, if you have any control valve, like a pressure reducing valve or something like that, or a filter station, you should have an air relief valve there. And then if you have a long main line, like on a lot of our larger agricultural projects, every 1,000 feet along that main line, be it even flat ground, you should have an air relief valve. This is a diagram I just needed to complete workshop I was recently working on, but what I wanted to show on it for winter time, but I wanted to show if you're putting valves above ground, this I thought was a good method of doing it. So what we're looking at here is we're looking at an electric valve here. The water is flowing up through here and going this way. When you're coming up, the piping that a lot of agricultural projects that I'm involved in throughout the Okanagan, large vineyards, large orchards, large vegetable growing operations, they're putting the valves above ground for ease of service. They don't care about the aesthetics necessarily, where they want that valve to be in a valve box. One of the challenges of any time you're putting the valves in a valve box, making sure it's large enough that you can properly service it. A lot of times people may want to save some money. They'll put a valve box that's just barely large enough to cover this valve here. Well, if you go to repair that and you're up against the side of a valve box, boy, you end up digging up that valve box anyway. So above ground is a benefit. The material that's used above ground should be a minimum of a Schedule 40 if you're using PVC pipe. I always like to see an isolation valve ahead of an electric valve. Why? They don't break down all the time, but they are going to break down, and it's a nuisance if you have to drain a whole main line in order to fix one valve, or if anything like that. If you can just isolate that valve there, or if for a period of time, do your repair on your system. This is making life a lot easier. This outlet here, there are systems where they'll need live water, like we're utilizing that for irrigation, sometimes out in the field. A lot of people are putting the live tap at this location here, so you always have live water ahead of your electric valve if necessary. And then your piping going down into the ground. In this instance, and a lot of things, I'll just point out one simple little thing here. If in this case here, this is a 2-inch pipe coming up, it's got a 1.5-inch electric valve. And I just know from this here that the flow going through the system is 50 gallons per minute of water. 50 gallons per minute of water requires a 2-inch pipe to feed it. So if you had a 2-inch piping system feeding this system here, when it goes down into the ground, the header line or the piping that feeds to your laterals is going to go in 2 directions away from that. It'll go this way and it'll go that way. What a lot of people will do is the piping going this way and this way may be smaller than the 2-inch. So let's say it's 1.5 inches. They put an 1.5 inch T on this pipe coming down. And then they would put one reducer, reducing this 2-inch to 1.5 inches, and then they would go 1.5 inch T at the bottom. That's not a very good way to do it. Why? I talked to you a little while ago about water hammer. Water hammer on a small pipe like that is going to really pay attention to a T or something like that, especially when it's smaller. That's where you're going to have a break. The T that should go in that system here should be a 2-inch T, and it should reduce on either side to 1.5 inches. So you've got a little bit of a cushion on that T that's going to protect it for that high volume of water on a water hammer. Leaks. Don't have to spend a lot of time on leaks, but I always like to bring up leaks because if you're irrigating in agriculture, your irrigation system is operating 24/7. It's operating for 24 hours a day, 7 days a week, and you have a leak. This is a leak from a traveling gun, or if you're just on a main connection like this. I go by so many orchards and I'll see a leak at the system, and the guy will say, well, it's just a little leak. Well, take a little leak. Let's say it's a little leak that's only giving you 5 gallons per minute of water out of it. 5 gallons per minute of water, that's 300 gallons in an hour over 24 hours. And if it's doing that the whole time throughout the season, you're wasting a good percentage of your water just through a leak. So any leak should be taken care of right away, and it sure impacts your efficiency of your system by not having it. So an irrigation assessment checklist, what the checklist is going to do is it's going to determine where you have potential problems in your system, how it's going to affect your efficiency. Because if that water is not efficiently going out to the system, especially if we get into situations where we have drought and the likes of that, where we have a shortage of water, we don't want to fall behind. So I just want to put 2 things on this slide. What is application efficiency? Is the percentage of actual water supplied by a system being delivered to the crop. The water that you have coming out of your point of connection If you have 20 gallons per minute of water coming out of your connection, is that 20 gallons per minute being delivered to your crop, or is it being lost before it gets there? Uniformity and efficiency, people get mixed up a lot. Irrigation uniformity is estimated variation on water volume between sprinklers or orifice devices on a system. In other words, it's a uniform system is going to have equal amounts of water being distributed through each sprinkler or each emitter through a system. That's how you measure uniformity. When we're looking at an irrigation system, be it a new system or whether you're planning to put in a system, we're going to look at all areas of the system. We're going to look at pressure at the beginning of the system. We're going to keep in mind the rise in elevation, how that's going to impact your pressure. We're going to calculate how much friction loss, which is the amount that's lost of friction as your pipe flows along your pipes through your main line and your laterals and even in the fittings. And then we will calculate that all out. So why is that important? If you want a uniform system, the water that's being delivered to the first sprinkler head or the first dripper on the system should not be to the very end, when you shouldn't have more than a 20% gain or loss in the system. And in some systems with drips, that might be 10%. You don't want to lose more than 20% of that water along that system, otherwise it's inefficient. You want to look at the size of the service, like I was saying before. If it's too small, is it going to be able to deliver the 25 gallons per minute of water? Let's say the water purveyor said you're allowed 25 gallons per minute of water. They've only gave you a 3/4 inch service. You might have a hard time getting that through that, depending on what your pressures are. So specifics of your system are important. The available flow is important. So specifics of your system may be you're only allowed to water for certain times of the day. How is that going to affect how you water? That specific may be your available irrigation window. So your bylaw in your area may be that you can only irrigate even your agricultural land for 12 hours a day. How is that going to work? You want to look at a system for hydrozones. What's the hydrozone? You know, on that first plan I showed you where I showed clay soils and sandy soils with the same crop. That's why I looked at breaking those zones up. It's called hydrozoning. That's why we do it that way. Microclimates. If you had a very large piece of property and you had some massive elevation changes, and you created different microclimate zones, or it was more of a shaded area, you'd be irrigating that separately. These are all the things that we'll be looking at to assess how efficient your system is. Now we're going to look at the types of devices that you're using for your different crops out in the field. And we're going to look at the different capabilities of them and what would be the best fit to your crops. The first two I'm going to show you, very few people are using them, but they are on this slide. And if you, let's say you're a 5-acre hobby farmer and you had access to a wheel move, it's something you may use. You see these on a lot of forage crops and that. They're being changed to a lot more sophisticated nowadays. You see a lot of wheel moves that are out there. I want you to keep track of this item right here, because for every different irrigation system that I'm going to show you, it's going to have an application efficiency on that. The higher this number is, the more capability of delivering that water in a smooth manner to your crops. So the challenge is with a wheel move system is the nozzles wear out on them. There's a lot of gaskets on them that wear out. The spacing of them and the uniformity of them all cause differences in the amount of water used from one end of it to the other. So for most of what we're going to be seeing, it's not the system that we'll be using for most of our gardens and that we're looking at today, but it has an application efficiency of 72%. The other area we're not going to spend a lot of time at all is traveling guns. And in saying that, you'll notice that on the initial drawing that I did do, I showed 1.2 acres where they were going to be planting corn, and I showed that in a traveling gun. Well, not one nearly as large as this. You can get very small guns right now, putting out 20 to 25 gallons per minute of water, let's say, that you could irrigate the most effectively for corn areas. So the main things in that case, again, you see how low this efficiency is. It's only 65% on a traveling gun versus the 72 on the wheel move even. But it may be the most effective, not efficient, but the most effective method of watering, say, corn or something like that. The size of the hose and the nozzles are the main things that wear out on guns. This is getting more into the line of what we're working on. A lot of conventional systems, and it depends on the crop, may elect to go to sprinkler systems. Sprinkler systems, you can get them in overhead, which are usually they're up higher, so they're averaging around 70% efficient. Under tree, which are closer to the ground, say 12 inches off the ground, can be as high as 75% efficient, more efficient systems. So what makes these systems work the best is spacing has to be right. How do you space sprinklers? What you usually do is we recommend to space your sprinklers at 60% of the diameter of the sprinkler head. So if you had a sprinkler head that has a diameter of 50 feet, then you would take 60% of that and you should be spacing those sprinklers at 30 feet apart. The height of the riser, obviously, is affecting your efficiency. So the height of the risers, a lot of times people will have heads up 7, 8, 10 feet in the air to get over top of their crops. That's going to affect their efficiency. The pressure on the laterals, what are those laterals doing? Are they going down steep hills? Are they going up hills? Or do you have issues like that? You want to look at differences in the pressure from these different sprinkler heads, how that's affected. Low head drainage, when that just shuts off, is all that water going to drain down to the bottom and cause puddling there? Uniformity, is our uniformity any good if our pressures differ that much along the line? Something as simple as heads being a level. A lot of times heads get bumped, get bent, or whatever, and so they're shooting off on the trajectory angle that's straight up. So it's not. So that's something that's got to be looked at. On a lot of systems, you're looking at part circle sprinklers and full circle sprinklers being on the same zone, which is fine, but do keep in mind the nozzles that are in a part circle sprinkler and a full circle sprinkler being operated together cannot be the same size. If you had a full circle sprinkler that had a 2 gallon per minute nozzle in it, or a 4 gallon per minute nozzle in it, and it's operating in a 360-degree pattern. If you put that same 4 gallon per minute nozzle into a part circle sprinkler, and it's only covering 180 or half the distance, you're going to be applying double the amount of water on the half circle as what you would for a full circle. Well, the remedy to that is if you had 4 gallon per minute sprinklers on a full circle and they're on a circuit with part circles, the part circle sprinklers should have 2 gallon per minute nozzles on it. Impact sprinklers versus stream. A lot of crops, vegetables even, are being used by, they want to use some overhead watering on them. The one thing I would caution is impact sprinklers are not good for that. The impact action, not only do you have to solidify them against the stake, but also the stream coming out of it, an impact sprinkler is a lot harder. It's going to do damage to your fruit and vegetables. So what's the answer to that? Modern day sprinklers, and I'm not advocating this particular manufacturer, but this is good quality sprinkler. It's called a rotator. They're using these in lieu of a lot of the brass impact sprinklers. These are being made now as the replacement for them. Why are they better? They design them as such that they fight wind better, because on some of these, the water coming out of this nozzle hits a baffle and breaks it up on different parts of the circle, so it's hitting the in close areas better. The uniformity of the sprinkler head is superior over that of its brass predecessors. So there are a lot of advantages. You can buy, for these sprinkler heads, pressure regulators that go on the base of the sprinkler head. So if you're going down a steep hill, that you're going to have the same pressure at the first sprinkler as you would at the last sprinkler because of the pressure regulation in here. You can also have check valves built into these sprinkler heads, and if the check valve is in there, it's going to eliminate that low head drainage at the low end of the system. These plastic heads are far more robust than the predecessors, and why I say that is a lot of people are still using a lot of hand move aluminum piping out in the field. And if you're dragging, or if you have a student or somebody dragging your pipes along and they're bumping them on the ground, if you have a plastic head that's got moving parts like an impact sprinkler, they're going to break. These are robust. This is guarded, your nozzle, your moving parts, so it's not going to break down. So, yeah, sprinklers have come a long way, and there are some excellent manufacturers out there. Micro sprinklers, as you can see on here, micro sprinklers, you can get them. What is a micro sprinkler? A micro sprinkler is a sprinkler that's using a significantly lower flow of water than that of a sprinkler head itself. Micro sprinklers, the benefit of that is a lot of times if you are applying water too fast, what happens is your soil cannot accept it at the same rate as what you're putting it down, and it's going to cause puddling. Micro sprinklers are always lower volume of throw, and they are used a lot right now in a lot of orchard crops, vineyard crops, and the likes of that. The one thing that's nice about them is you can see up here, there's two types of micros. One is a spray, like you can just see it's the consistent spray, solitary, so it isn't moving. Water's just coming out of it. Versus a micro sprinkler, where it is again at low pressures. Low pressures, I mean below 30 pounds pressure. At low pressures, so it's going to do a better job of distributing the water. But the micro sprinkler is going to throw water for the micro spray, but it is a little bit more efficient, that big spray. 85 versus 80%. One thing you have to watch is micro sprinklers, smaller flows, smaller orifices, so your filtering has to be of the right size. Lateral tubing, it's critical the size you use in that, because as I said earlier, say in micro sprinkler system, you don't want to lose more than 20% of your pressure along the line, so it means you may have to put larger tubing. Blockages in your pattern, that's one thing I see a lot in orchards, where if you have a branch or something like that that sticks into the micro sprinkler, won't turn. It's going to be always putting water on the trunk of the tree. It's not good. You have to make sure that they're level. The uniformity is good in micro sprinklers. Nozzle sizing is important. One thing I will mention right at this point is I've seen a lot of systems over the years where micro and drip irrigation systems are supposed to be so efficient, and if installed and applied properly, they are. But like anything else, they can be abused. I've seen micro systems that may start out as sprays, then all of a sudden they run out of water, they change to drip, and they might change to something else along the way, and they go too long. So they are too much plug and play versus a sprinkler system that's buried in the ground. So keep consistent, whatever you're utilizing on it, keep the same product all the way along the line. So you're going to maintain consistency and uniformity. Drip irrigation system. Well, a lot is, you can see a drip irrigation system is 90% efficient. It's probably, from that perspective, best system on the marketplace. Drip is putting water down at a very slow rate. It's efficient because where is it applying the water? In this case here, just look at one of these pipes for now, please. It has most of the drip irrigation we're using nowadays isn't the style of the punch-in style where you're actually pushing an emitter wherever you so desire it. We are consistently, this type of a system, purchasing a tubing that has emitters pre-installed at varying measurements. So in an orchard or something like that, we may have an emitter installed inside of the line every 2 feet along the line. If we're dealing with vegetables or something like that, emitters might be 12 inches and 6 inches apart. The water is being consistently applied slowly right to the root zone of the tree, increasing the efficiency of it. And most of these nowadays are pressure compensating. Downside of all of this goodness is the emitter orifice size, even smaller yet. So you've got to be cognizant of the filters you're using, and also making sure that your filters are large enough, as well, but you're not having to clean them every couple times a day. So that's the big nemesis. You're going to need that fine filtration, and for drip irrigation, just make sure you have a large enough filter to facilitate that, or go to an auto flushing filter. A lot of people don't have backup screens on lateral lines going into drip, and I highly recommend it. So if right here, this is the beginning of that line, and it's coming off of your valve is here, and it's coming off of what I call a header line to join them all together. I recommend on drip to consider putting a little screen on the beginning of that line there. Why would I do that? Well, if you have a break in your main line or your sub mains, where does all of that debris migrate to? Into these lines. So even if you have the best filter system in the world at the beginning of the system, if you don't have something down here, a lot of that could still get into drip is important. You're going to notice here we got two lines. Why? Because a lot of people right now, they're saying, well, the drip system is good, it's not applying enough water, or the time of the year when I need a lot of water just before harvest on the crops, that's necessary. How am I going to do it? Double row of drip allows more water to the root zone, both sides of it. What a lot of people are using. Commonly, they'll be irrigating with one line, and then when they hit peak watering, they'll put two lines into irrigating.
Hey, Bruce, sorry
Yes.
to interrupt. I just wanted to give you a time check. We've got about 20 minutes left. So just to keep that in mind in case you want to do the question and answer section.
Yeah, this section here, I'll go very quickly. I'll be finished this in 5 minutes. So.
Awesome.
Okay, so subsurface drip irrigation system. The most efficient system of all is the subsurface drip irrigation. Well, that's the same system right now, except you're burying it down in the ground. Great, you go from 90 to 95% efficient, but then you have big problems with not seeing what the system is doing. So that you don't know if it's actually working, as well as a lot of rodents that are going to affect you. So there's a lot of different methods out there to control that. Some companies are utilizing what's called a copper oxide that's going. It's being installed. The little copper wire is time as the emitter is being put in, and the copper deters the from growing into the outlets of the drip emitters. You can get some with check valves and likes of that. That is always the downside of going to a subsurface drip system. They're being used a lot more right now, even on crop areas where they were using traveling guns and that down in the States, cotton and different crops like that. They are using drip irrigation in some circumstances where there's a water shortage or pressure shortage. So this is an idea of what the system will look like. The machine will pull all these lines in 24 inches apart, 18 inches apart, depending on the crop, and at a depth be below the active working areas. So if you're prodding into the ground, it would have to be a foot at least down in the ground. So, but it's something that some people are doing right now. So selecting the best crop for your system, filtration is important. Water treatment may be important. You want to look at the volume of water you have available, pressure you have available. If it's too low, you may want to look at a drip irrigation. We haven't got a lot into crops right now, but different crops require the replacement of more water than others. Crops that you are planting, make sure you have enough water available for that. Yeah, you're also going to be looking at what are you going to be using that system for. Like if you're using a system where you want to have panels in between, like tree fruits and the likes of that, you may want a cooling system. The cooling system is at the middle, so you may be more apt to use an under tree sprinkler system or micro sprinkler versus drip. Retrofitting into a system, you have to be careful what you're doing, making sure everything is of the right size to do that. Soils may make a variance on what you decide to do. If you have a real heavy clay soil that's not going to accept the water too fast, that may make you want to go to a micro or a drip type of. Length of your rows, like in vineyards, or elevation changes, they're quite dramatic, so you've got to keep that in mind when you're selecting a system. And there's available funding to prepare a lot of things from the environmental farm plan or anything to improve irrigation efficiencies. That's something we could talk about that too. Different tools that are useful for irrigation purposes. weather stations are great, but they're expensive. There's Farm West is out there. It's a service that's available. Get your daily evapotranspiration rates. That it'll help you to schedule your irrigation system. This isn't the time to talk about it a lot, but you might want to visit farmwest.com. It's a useful site. Smart irrigation controllers. There's something that I was talking about earlier, like the ability with the flow sensors to be able to shut this off. That's a smart irrigation controller. You can get ones with Wi-Fi capabilities, so you can run them off of your tablet or your phone. Also good. Two-wire systems are really a good idea. Two-wire system, instead of having to have a separate wire to every individual zone, you have a two-wire system. You can run up to 100 zones off of 2 wires on a system. So a lot of larger projects are going that way. Here's a little device that you can use. So it's like a mini weather station. It's a solar sink made by one company. So it's got something that's mimicking evapotranspiration. It's collecting how much water catchment you have in an area there, and it's modifying your runtime. So if you had your drip irrigation set to water for an hour a day, and this sensor may pick it up, and you've had enough rain in the last little while that it may reduce it to half an hour or something like that. Something could be something. You can also get those for soil sinks, which is actually the moisture sensor, soil sensor, like a watermark sensor that goes in the ground, gives you a reading. You can use that, which is probably one of your best ways of gauging water. This is the flow sink, or the flow sensor I was talking about. It just goes into a T into your line, and it, with these wires, can hook to a controller and give you what your flow of every individual zone is. This is a little paddle wheel. It turns around. The RPM that it turns, that correlates to a flow. Proactive measures to minimize drought impacts. Depending on your crop, if you have a deep root zone, then you can get water early. Start watering earlier. Fill up your root zone so that all you're doing is topping it off with your irrigation system when you get into a drought condition. Soil moisture sensors should be evaluated and put into different grounds. It's an excellent way of staying on top of things, knowing what's going on down the ground. Soil amendments are always going to help for holding that moisture in your ground at the end of the season. Mulching and cover crops. And like I was talking about a little earlier, if you don't have the water available, instead of planting that whole 5 acres, maybe reduce it by 1 acre so you can properly irrigate the area that you want to grow your crops on. Lower volume with higher yield could give you the same end result. Okay, so here are some questions. I'm gonna, do you want me to read these first, Teresa, or maybe we could take it from the field and come back to this? If it's time.
Sure, we can do that. At this point, I'll just thank you so much, Bruce, for your presentation, and I'm just going to stop the recording so that people can freely ask questions.